So now we'll turn our attention to a very common type of series that you'll run into, which is called a geometric series. And the thing about a geometric series is that it's very predictable and very easy to determine if it's going to converge or not. You may have run into geometric series in the past, but they are series that are of the form uh, n equals 1 to infinity of a times r to the n minus 1 power. So what that looks like is if we let n equals 1, we would have a times r to the 1 minus 1, which is a times r to the 0th power, which is just a. So the first term in this sequence is a. The next term in the sequence, when n is 2, would be a times r to the 2 minus 1, which is a times r to the first, or just a times r. And then this pattern would continue, a times r squared, a times r cubed, and so forth. Now, it's actually the same series, and some textbooks actually do it this way, as the sum n equals 0 to infinity of a times r to the n. And in fact, that's the way that I was taught, and that's the way that I'm more comfortable with. Uh, Either way is perfectly fine. It means the exact same thing, because where your starting value is doesn't really make a difference as long as the terms are the same. And they are, because if you let n equal 0, a times r to the 0 is still just a for the first term, and then a times r, and so forth. So these are identical. Now, the reason that I said that this series is so predictable and easy to determine if it converges or not is because all you have to do is look to the value of r, and that's called the common ratio. And if the absolute value of r is less than 1, then we know that that series converges, and we actually know what it converges to. It converges to this value, a divided by 1 minus r. And that's true, doesn't matter which form you're using here. So even if you're starting with n equals 0 and using a exponent of n. And then if the absolute value of r is bigger than 1, the series diverges. Okay, so let's get an idea as to exactly why that is. So to help us determine this, it's useful to determine some partial sums here. So the first k partial sums would be the sum from n equals 0 to k of a times r to the nth power. Sorry, that's still going to be n right there. Okay, now if I start writing out what the first k sum values are, I could say s of k would be equal to, so when n is 0, this would be a times r to the 0, which is just a. When n is 1, it's a times r, so plus a times r, plus a times r squared, plus a times r cubed, and so forth. Oops, not a cubed, a times r cubed, and so forth, out to a times r to the kth power. All right, because k is where I would stop for a finite sum here. Now, this next step is really just kind of a trick to get things to cancel, okay? But it's a worthwhile trick to use in this particular case. If I subtract r times s of k, here's what's happening. Each of these terms in s of k, so a times r squared, all of them get multiplied by an additional factor of r and get negated. So a times negative r would be negative ar. Ar times negative r would be negative ar squared, and then negative ar cubed, and so forth. And the positive ar cubed would become minus ar to the fourth, and then all these terms in between. And eventually I would get over here to minus ar to the k plus 1, because this term right here, this very last one, a times r to the k, when I multiply it by negative r, I would have negative a times r to the k plus 1. Okay, now, if I subtract, On the left-hand side, I end up with something that looks like s sub k minus r times s sub k. But on the right-hand side, I get all kinds of things that cancel. Those two terms cancel. These cancel. These cancel. And even though I haven't written it, there would be a term up above here somewhere that would match the ar to the fourth. And likewise, even though I haven't written it, there would be a term that would match down here somewhere, ar to the k. There wouldn't be a matching term to the minus ar to the k plus 1, however. So the sum of all these would result in a minus a times r to the k plus 1 power. But this is kind of a neat situation here. I have a simple formula here. In both the left and right-hand sides, there's common factors that I can pull out to simplify. So I can pull out s sub k from the left-hand side, leaving me with 1 minus r. And I can pull out an a from the right-hand side, leaving me with 1 minus r to the k plus 1. And if I divide both sides by that 1 minus r, what I end up with is s sub k equals a times 1 minus r to the k plus 1 all over 1 minus r. And this is a neat formula. This is a formula for the sum of the first n terms, well, I should say k terms because n is my exponent. So the first k terms of a geometric series. And this is a finite geometric series, so that sum would always exist. Okay? Now, if I wanted to do an infinite series, right? So if I wanted to make this an infinite series, and that's what we're aiming towards, so absolutely what we want to do, I would need to look at the limit as k goes to infinity of this sum, so of a times 1 minus r to the k plus 1 all over 1 minus r. And the constant a and the 1 minus r would be a multiplier, which I could pull out, not r minus 1, sorry, 1 minus r. And then that's times the limit as k goes to infinity of just what's left, the 1 minus r to the k plus 1. Okay, now I don't really have a very strong argument as to what exactly happens next, but I think you can follow along here and understand. So this term right here, if I'm letting k go to infinity, what I want is this limit to exist. So I want it to converge to a real number. So the thing is, if it's going to converge to a real number, it all kind of depends on, what happens with r here, because clearly the 1's going to converge since it's just a constant. But raising something to the k plus 1 power where k keeps increasing, so I have like some value to the first, some value squared, some value to the third, some value to the fourth. I'm adding these larger and larger and larger powers. So if r is bigger than 1, clearly this thing is going to diverge because I'm taking larger and larger numbers. I'm taking numbers and raising them to powers, and they get larger and larger and larger. So clearly it's going to diverge at that point. And also, if r happens to equal 1, well then in that case, it's easier to just go back to the original sequence. And if you think of r as being 1, then 1 to any power would be just 1, which seems like it's converging, but the thing is, your sum would be a plus a plus a plus a plus a, which would not converge. All right, so we can rule that out. All right, however, if r happens to be less than 1, and in fact, it could be somewhere between -1 and +1, so which is why we say if the absolute value of r is less than 1. Then what we end up with is something that could probably be written as a fraction. Just think of it like that. All right, so if I have a fraction, so let's say if r is equal to a half, then I'm taking 1/2 and raising it to increasing powers. which means I'm actually taking 1 over 2 to some increasing power. So I have a fraction where the denominator is changing, the numerator is not. So what happens there is under this condition, if r is the absolute value of r is less than 1, this term goes to 0. And if that goes to 0, this limit is just 1 because k is not changing anywhere beyond that. And you just have 1 times the a times 1 minus r. So under that condition, what happens is this converges to a over 1 minus r, just like the formula states. So, like in an example here, determine whether the following geometric series converges or diverges, and if it converges, find its sum. All right, so notice here that this particular series begins at 0. That's okay. It can start at 0, it can start at 1. It really could have any starting point. Everything's going to work out just fine either way. What I need to do here is figure out what to do with this n plus 2, however, because the formula up here doesn't say what we can do with n plus 2, for instance. So here, I can do this. I can say this is the sum as n equals 0 to infinity of 2/3 to the n times 2/3 squared. Now, why can I do that? So that is a property of exponents, where if you have some value raised to an exponent times some other value of the same base with a different exponent, you can combine those by adding the exponents together. But the reverse is true as well. So if you have an exponent that's added, you can split it up into two exponentials with the same base that are multiplied. Okay? And 2/3 squared is a constant. It just works out to be 4/9. So then I have 4/9 of the sum n equals 0 to infinity of 2/3 to the n. And as I mentioned, you can have this formula working in this form, n equals 1 to infinity of a times r to the n minus 1, or you can have it working n equals 0 to infinity of a times r to the n. Either way is the same. It's just a different starting point, but they all have the same terms. And because of that, I can now determine that this series right here is geometric. And because it's geometric, I can identify the value a. Well, a in this case, I actually could have used a as 4/9, but I pulled it out of the sum, so it doesn't really matter. What's most important is r. R in this case is 2/3. And that is less than 1. And because it's less than 1, this series converges. And it converges to a over 1 minus r. And all I need to do is just simplify this and just take a second with some fractions. So let's see, 4/9 times 1 over 1 minus 2/3 would be 3/3 minus 2/3, so 1 over 1/3. So 4/9 times 3. 3 goes into 9 3 times, so this is ultimately 4/3. So what that means is I have a geometric series that converges to the value 4/3. Okay, let's take a look at another example. So in this next one, it's the same thing. Determine whether the following geometric series converges or diverges, and if it converges, find its sum. Well, this one's already set up directly to solve. We have n equals 1 to infinity of 1/9, and then the exponent, notice, is n minus 1. That's equivalent to it being n when you're starting with 0. So it's geometric. The value of a is 1 again. The value of r is 1/9. And that is less than 1. So that tells me that the sum of this is a over 1 minus r. So that's going to be 1 over 9/9 minus 1/9 would be 8/9, or 9/8. So it's a geometric series that converges to the value 9/8. Determine whether the following geometric series converges or diverges, and if it converges, find its sum. So same problem as previous, but just different example here. Here I'm starting with n equals 0, so my exponent should be n. Right now it's 2n, but we can use rules of exponents as we please here. So like e to the 2n could be written as e squared to the nth power, because rules of exponents say that if you take something raised to an exponent and then raise it to another exponent, you can simplify that by multiplying those exponents. But you can, of course, go the other direction as well. So this would be the sum, n equals 0 to infinity, of e squared to the nth power. So what that means is this is of the form of a geometric series. And the value of a, again, there's no constant here except for just 1, but r is e squared. Now, e squared, you might not recognize what that particular value is, but you should know that e is approximately 2.718. So if you square that, you're certainly going to get something bigger than 1. It turns out e squared is about 7.39, but regardless, it's bigger than 1, so that tells me that this series diverges. So when r is larger than 1, we have a diverging geometric series.